Swayam Prabha. Digital India. Educated India.
Welcome to lecture 11 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Model with Heteroscedastic Disturbances. In the last lecture, we considered general linear regression model in which the disturbances are non-spherical. When the disturbances are non-spherical, the OLS estimator still remains unbiased and consistent, but the blue property of the OLS estimator is lost. So, it is not an efficient estimator. Then as an alternative, one may consider the generalized least square estimator. We also proved the unbiasedness and consistency of the generalized least square estimator, and we also observed that the GLS estimator satisfies the blue property. Now, two of the special cases of model with non-spherical disturbances are the model with heteroscedastic disturbances and the model with autocorrelated disturbances. In this lecture, we are going to consider the general linear model with heteroscedastic disturbances. In the model with heteroscedastic disturbances, the assumption that the disturbances have common variance, constant variance is not satisfied. In practical applications, in many practical applications, you may observe that the disturbances are not homoscedastic, but heteroscedastic. We considered an example also in the last lecture, where we have income and family expenditure data, and then the families belonging to lower income group have lower variability in the food expenditure in comparison to the families belonging to the higher income group. The families belonging to the higher income groups have more variability in the food expenditure. So, now I am going to consider the general linear regression model with the heteroscedastic disturbances. We will consider the problem of estimation of regression parameters for these models. We will also discuss different tests for testing the heteroscedasticity or homoscedasticity of the disturbances. So, we consider the model y equal to x beta plus u, and then the assumption of spherical disturbances is expectation of u transpose equal to sigma square u I n, or expectation of u I u j is equal to sigma square u if I is equal to j, and it is 0 if I is not equal to j. Then the disturbances which have constant variance across the observations are termed as homoscedastic disturbances. If this variance is constant across the observations for all i's, then we say that the disturbances are homoscedastic. But if the disturbances do not have constant variance across the observations, then the disturbances are called heteroscedastic disturbances, and the disturbances which are pairwise correlated are termed as autocorrelated disturbances. So, we get these three situations: homoscedastic disturbances, heteroscedastic disturbances, and autocorrelated disturbances. And then you have the four possibilities: disturbances are homoscedastic and pairwise uncorrelated. Disturbances are heteroscedastic and pairwise uncorrelated, means for different i's, ui's have different variances. Disturbances are homoscedastic, means expectation of ui square is equal to sigma square u for all I, but pairwise correlated. And the fourth possibility is that disturbances are heteroscedastic and pairwise correlated also. Now, suppose in model 1, expectation of u I u j is equal to sigma square I for all I equal to j, and it is 0 for I not equal to j. Then expectation of u transpose is equal to omega, which is a diagonal matrix with diagonal elements sigma 1 square, sigma 2 square, so on sigma n square. So, omega is a diagonal matrix. Again we consider this example. Suppose x 2 denotes the family monthly income, and y is the family monthly expenditure on food, and the model for expenditure equation is yi equal to beta 1 plus beta 2 x 2 I plus ui for all I equal to 1 to n. So, this is your model. Here family income is your explanatory variable and family monthly expenditure on food is your variable to be explained by the model or dependent variable. Then usually as income increases, the expected expenditure on food usually increases. Not only that, but the variation in expenditure on food also increases. Again, the families belonging to the lower income group, usually they have some financial constraints because of lower income. So, normally for food they do not have many options, they usually go for cheaper food. So, you may find lesser variation in their food expenditure. So, if you have monthly data, then you may also for lower income groups you may not observe too much of variation. For families belonging to the higher income group, they do not have such kind of financial constraints. So, they have a lot of options. So, in some particular month they may go for some expensive foods, or in some other months they may go for some cheaper food. So, they do not care if the price of mango in September is 400 rupees per kg, still they can expend and they can buy mango in September or October also. They do not have financial constraints. So, you may observe a lot of variation in their food expenditure. So, the variance of ui also depends upon the income. So, you can say that sigma square I is equal to sigma square u into x 2 y, that is variation is proportional to the income, and in this case the variance coefficient matrix of u is sigma square u into diagonal x21, x22, so on x2n, which is equal to capital sigma or sigma square u omega. Omega is this diagonal matrix. So, actually this income plays two different roles in your model. Income is an explanatory variable in the expenditure equation. Say here this x2I is an explanatory variable, and then income is also causal factor in the heteroscedasticity process. It is causing the heteroscedasticity in your model. So, in this sense the income is playing two different roles in your model. It is playing the role of an explanatory variable in the expenditure equation as well as the causal factor in the heteroscedasticity process. Now, we take another example. In modeling a state domestic product of different states of India, the variability usually increases with state's size. So, if your dependent variable is a state domestic product, then for the states with bigger size like UP, you may observe more variability. But if we model per capita SDP, then it may have homoscedasticity. So, different states have, means if you are modeling per capita SDP for different states, then you may observe homoscedasticity. So, per capita SDP does not have the problem of heteroscedasticity. So, in this particular problem we are observing heteroscedasticity because of incorrect data transformation. So, instead of modeling state domestic product, one should go for per capita SDP. Now, the OLS estimator of beta is B equal to x transpose x inverse x transpose y, and its residual is E equal to y minus x b, and we write it equal to E1 E2 En transpose. Then the properties of OLS estimator under heteroscedasticity. OLS estimator is still unbiased and consistent. Actually, the model having heteroscedastic disturbances is a special case of model having non-spherical disturbances, which we have discussed in the last lecture. And in the last lecture, we have proved that the OLS estimator is unbiased and consistent even for the model with non-spherical disturbances. So, here also OLS is still unbiased and consistent, but the OLS estimator for non-spherical disturbances is not efficient. It does not satisfy the blue property. Here also OLS estimator is inefficient. Again, the conventional test statistic based on OLS are not valid. Now, the variance covariance matrix of B is x transpose x inverse, x transpose sigma x, x transpose x inverse, where sigma is the diagonal matrix having elements sigma 1 square, so on sigma n square. Now, this is not equal to sigma square u x transpose x inverse. Now, suppose you want to estimate this variance covariance matrix of B. So, still you are using B to estimate beta, and then you are also interested in estimating the variance covariance matrix of B. Then the variance covariance matrix of B involves this sigma. So, actually you have to estimate this sigma, but the problem is that sigma is a diagonal matrix having n elements sigma 1 square, sigma 2 square, so on sigma n square. So, it has n parameters, and then you have n observations. So, on the basis of n observations, you cannot estimate all these n parameters. Remember, you also have the parameters beta 1, beta 2, beta k, the regression coefficients. So, on the basis of n observations, you cannot estimate all these parameters. Now, suppose we write x j transpose equal to say 1 x 2 j so on x k j transpose. Then x transpose sigma x is equal to summation j equal to 1 to n sigma j square x j transpose. Then White in a paper in 1980 published in Econometrica, he stated that one requires estimate of x transpose sigma x, which is of order k by k, and it is independent of n. It does not involve n. If you are directly estimating sigma, then it may not be possible for you to estimate sigma directly, because the sigma involves n parameters. But if you estimate x transpose sigma x, then this is of order k by k. So, you can estimate it. It is possible for you to estimate it, and you can find a consistent estimator of it as, so x transpose sigma hat x equal to summation j equal to 1 to n e j square x j transpose. Now, this is a consistent estimator of x transpose sigma hat x. Again, I am not going into the details of proof. Then an estimate of variance covariance matrix of B is x transpose x inverse x transpose omega hat x, which you get from here, x transpose x inverse. So, you get an estimator for the variance covariance matrix of the OLS estimator B. This estimator is called the White estimator. And suppose you want to test the hypothesis H naught r beta equal to small r. Then the Wald test studies for testing this general linear hypothesis is W equal to R B minus small r transpose. Then in between we take R, then we take estimate of the variance covariance matrix of B here, which is given here, R transpose R B minus small r, and this follows a chi-square distribution with q degrees of freedoms. So, instead of using the earlier statistic which we have derived for the model with the homoscedastic disturbances, one can use this statistic W, which is also based on the OLS estimator B, for testing the general linear hypothesis R beta equal to small r. And since this statistic follows a chi-square distribution, you can easily form the critical region for testing this hypothesis. Now, we consider the grouped or replicated data and the problem of heteroscedasticity for grouped or replicated data. So, suppose we have n observations on G groups. So, basically these n observations are divided into G groups. It is just like we divide the income data into 3 groups: higher income group, middle income group, and lower income group. So, we have divided all these n observations into G groups. The ith group has ni observations. I varies from 1 to G. So, obviously, n is equal to summation I equal to 1 to G ni. Or you can say the observations of the ith group are replicated ni times. You have G group, you are taking observations from these G groups and you are replicating the observations from the ith group ni times. So, we have replicated data. Then the disturbances variance varies in different groups. So, we assume that for different groups we have disturbances variance. Then the model is say y1, y2, yg equal to x1, x2, xg beta plus u1, u2, ug. Again this vector y is of order n cross 1, this x matrix which is consist of x1, x2, xg is of order n cross k, again u1, u2, ug, this is of order n cross 1. Then yi is of order ni cross 1. So, basically here we have n1 observations, n2 and so on, n g, and summation ni is equal to n. Then expectation of ui transpose is equal to sigma square I ni. So, actually sigma square I is the variance of observations for the ith group, and expectation of ui uj transpose is equal to 0 for all I not equal to j. So, different observations are uncorrelated with each other, or you can say different groups are also uncorrelated with each other. Then expectation of u transpose, say you write it equal to capital sigma is equal to sigma 1 square I n 1, sigma 2 square I n 2, so on sigma g square I n g. So, it is a diagonal matrix. First n 1 diagonal elements are sigma 1 square, next n 2 diagonal elements are sigma 2 square, and so on. Last n g diagonal elements are sigma g square, and all the off diagonal elements are equal to 0, because there is no correlation in disturbances is involved. Then the OLS estimator is inefficient because it does not satisfy the blue property. The GLS estimator of beta is beta hat equal to x transpose sigma inverse x inverse x transpose sigma inverse y, and let us write it equal to x transpose omega inverse x transpose omega inverse y. Actually, we have replaced the sigma by omega here. Still this estimator is not feasible in the sense that this omega involves the parameters sigma 1 square, sigma 2 square, so on sigma g square, which are unknown. So, for obtaining the feasible generalized least square estimator, you have to estimate these parameters, these sigma square i's, and then you have to replace these parameters by their estimators in this expression for the GLS estimator. So, these are the steps for obtaining the FGLS estimator for grouped data. So, first we obtain the OLS estimator of beta I based on the ith group. So, the ith group is yi equal to xi beta plus ui, and when we apply OLS to this particular ith group, we get bi equal to xi transpose xi inverse xi transpose yi for all I equal to 1 to g. And of course, you can apply the OLS procedure for estimating beta for the ith group, because for a particular group or for the ith group, the assumption of homoscedasticity is satisfied. So, you can apply the OLS procedure, and it is efficient also for a particular group, and then we calculate the OLS residuals for the ith group. So, EI is equal to yi minus xi bi. This is the OLS residual for the ith group. Then in the next step, we use this OLS residual for estimating sigma square I, the variance or the estimate of the variance for the ith group. And the estimator is Si square equal to Ei transpose Ei upon Ni minus k, which is equal to 1 upon Ni minus k y minus xi bi transpose y minus xi bi. Of course, here we assume that all the Ni's are greater than k. This is the assumption which we require. So, in each group we must take the number of observations greater than the number of explanatory variables k. Or suppose you want to go for the maximum likelihood procedure, then you can estimate sigma square I by sigma hat square I equal to Ei transpose Ei upon Ni. Then we replace sigma square I by Si square in the expression for sigma, and so we obtain sigma hat, the estimator of sigma. And then to obtain the FGRS estimator of beta, we replace sigma by sigma hat in the expression for beta hat. Beta hat is equal to x transpose sigma inverse x inverse x transpose sigma inverse y. So, we replace this sigma by sigma hat, and then we obtain this feasible generalized least squares estimator. Now, the next problem is to test for the heteroscedasticity for the grouped data. So, for that purpose one can use Bartlett test for testing the heteroscedasticity. So, basically we want to test the null hypothesis H naught sigma 1 square is equal to sigma 2 square, so on equal to sigma square g against the alternative hypothesis H 1 that H naught is not true, means at least one of these equalities does not hold. Then to apply the Bartlett test, we obtain Si square equal to 1 upon Ni minus k y minus xi bi transpose y minus xi bi. And for obtaining this estimator, we use the steps 1 and 2, and then we obtain S square equal to summation I equal to 1 to g Ni minus k Si square divided by summation I equal to 1 to g Ni minus k. So, we calculate this S square. Now, once we calculate S square, then the test statistic is say chi square equal to 1 upon capital C summation I equal to 1 to g Ni minus k S square upon Si square, and this follows a chi square distribution with g minus 1 degrees of freedoms under H naught. Here C is equal to 1 plus 1 upon 3 g minus 1 summation I equal to 1 to g 1 upon Ni minus k minus 1 upon summation I equal to 1 to g Ni minus k. So, this is the value of C which we can use here. Again, I am not going to give you the derivation of this distribution of the test statistic, but using this distribution you can easily form the critical region for testing H naught. So, this is the calculated value of chi square, and then we reject H naught at 100 alpha percent level of significance if this calculated value of chi square is greater than the tabulated value of chi square at alpha level of significance. So, this is the critical region. Now, if it is not possible to replicate the data, then of course, you cannot apply this test, or the data is not grouped data, then this procedure fails. Then you have to go for some alternative test procedure like Bruce-Pagan test, or later on we will discuss some other test procedures also for the data which are not grouped data or not replicated data. Now, we consider the weighted least squares procedure. Now, suppose expectation of ui square is equal to sigma I square, and sigma I square is equal to sigma square u omega I for all I equal to 1 to n, and ui's are pairwise uncorrelated. Then expectation of u transpose is equal to sigma equal to diagonal sigma 1 square, sigma 2 square, so on sigma n square. Then we substitute the values of sigma I squares here. So, we get sigma square u diagonal omega 1, omega 2, omega n, which is equal to sigma square u omega. Now, if we take 1 upon under root omega I u I, then this has variance sigma square u. So, what we do? We multiply say y 1 by 1 upon under root omega 1, y 2 by 1 upon under root 2 omega 2, and so on y n by 1 upon under root 2 under root omega n. Similarly, we divide x 1 by under root omega 1 and so on x n by under root omega n. So, basically we get p y and p x, where P is a diagonal matrix with elements 1 upon under root omega 1, so on 1 upon under root omega n, and then we obtain the weighted least square estimator of beta as beta hat equal to summation I equal to 1 to n w I x I transpose inverse summation I equal to 1 to n w I x I y I, where w I is equal to 1 upon omega I. So, we get this estimator, which is the generalized least square estimator. Here actually you are having these weights w i's here, and w I is equal to 1 upon omega I. So, in weighted least square estimator, y i's with smaller variance get larger weights. Suppose omega 1 is small. So, y 1 has a smaller variance, and then the weight is w 1, which is equal to 1 upon omega 1, and then y 1 gets the weight w 1. So, y 1 gets larger weight. So, y i's with smaller variance get larger weights. Now, we consider another case. Suppose sigma I square depends on a regressor z I through the relation sigma I square is equal to alpha naught plus alpha 1 z I to the power alpha 2. Say for example, in the income and food expenditure data example which we discussed earlier, you may take sigma I square as proportional to the income, say x to I, or you may take sigma square I equal to some constant time, say alpha 1 x to I, or suppose sigma I square is proportional to x to I square, then sigma I square may be equal to alpha 1 x 2 I square, or you may introduce alpha naught here also. So, at least even for alpha 1 equal to 0, you get this much of variance or this much of heteroscedasticity. So, we are taking sigma I square equal to alpha naught plus alpha 1 z I to the power alpha 2 for all I equal to 1 to n. Then if we have alpha 1 equal to 0, this leads to sigma I square equal to alpha naught. So, we have the case of homoscedasticity. All the sigma i's squares are equal to alpha naught. If we take alpha naught equal to 0, alpha 2 equal to 1, then this leads to sigma I square proportional to z I, the case which we have discussed here. Or if we take alpha 2 equal to 2, then this leads to sigma I square proportional to z I square. Say for example, if sigma I square is equal to alpha 1 z I, then capital sigma is equal to alpha 1 into diagonal z 1 z 2 z n, which is equal to alpha 1 omega. And in this case, x transpose omega inverse x is equal to summation I equal to 1 to n z I inverse xi transpose, and x transpose omega inverse y is equal to summation I equal to 1 to n z I inverse xi yi. So, you can obtain x transpose omega x inverse also from here, and then you have x transpose omega inverse y also here. So, you can obtain the GLS or weighted least square estimator of beta as beta hat GLS equal to x transpose omega inverse x transpose omega inverse y equal to summation I equal to 1 to n z I inverse xi transpose inverse summation I equal to 1 to n z I inverse xi yi. So, this is your GLS or weighted least square estimator of beta. So, basically in this case, if you compare it with this expression, then we have taken omega I equal to z I. In general, suppose we consider this case, say sigma I square is equal to alpha naught plus alpha 1 z I to the power alpha 2. Then how we proceed? Then we use nonlinear regression to fit this model. In 15, we replace sigma I square by the OLS square of OLS residual E I square. E I is the OLS residual. So, we use this equation and then we run nonlinear regression, and we estimate alpha naught head, alpha 1 head, alpha 2 head from here. And once we estimate alpha naught head, alpha 1 head, alpha 2 head from here, then an estimate of sigma I square is sigma head square I is equal to alpha naught head plus alpha 1 head z I to the power alpha 2 head for all I equal to 1 to n. So, this is how you can estimate sigma head I square. Now, we consider different tests for testing the heteroscedasticity. So, first we consider the white test. Now, suppose we want to test the hypothesis H naught such that sigma I square is equal to sigma square u for all I equal to 1 to n against the alternative that H naught is not true. So, basically you are interested in the hypothesis sigma 1 square is equal to sigma square 2 equal to sigma square n, and this is equal to sigma square u. Say. Then first we obtain the OLS residual. We simply run the OLS over this model, and then we obtain E. E I is equal to y I minus x I transpose B is the ith element of E. So, this is the OLS residual. Then we regress E I square on the squares and cross products of the regressors 1 x 2 so on x k. So, we just write 1 equal to x 1. So, we denote this 1 corresponding to the intercept term by x 1. So, we have the regressions x1, x2, so on xk. So, now we take x1 square, x2 square, xk square, and then we take the cross product terms x1, x2, x1, x3, x1, xk, then you have x2, x3, x2, xk, and so on. So, basically we take all the squares and cross products of these regressions, and we run regression of EI square on all these squares and cross products of the regressions. So, in all, how many terms you have? K into k plus 1 by 2. In fact, this is equal to Kc2, and Kc2 is equal to k into k plus 1 by 2. And then we obtain the coefficient of determination r square. This coefficient of determination is obtained by running the regression of EI square on all these squares and cross products. Then the white test statistic is n times r square, and under the null hypothesis of homoscedasticity of disturbances, this n times r square follows a chi-square distribution with k into k plus 1 by 2 minus 1 degrees of freedoms. So, now you can easily form the critical region. Say if n r square is greater than the tabulated value of r square, say alpha k plus 1 by 2 minus 1 is the degree of freedom, then we reject H naught. So, this is the critical region. Now, this white test is a quite general test, and it may be used to test any kind of heteroscedasticity. Notice that we have not assumed any form for sigma I square, like sigma I square is proportional to something or anything like that. But the problem with this test is that the test may reject H naught when there is a different specification error, or the power of the test may be low, particularly when k is high. Remember that we are regressing EI square on k into k plus 1 by 2 in terms involving squares and cross products of x's. So, the power of the test is quite low if k is high. Now, we come to the Bruch-Pagan test. In Bruch-Pagan test, we assume that sigma I square is equal to H Z I transpose alpha, where Z I transpose is this p cross 1 cross p vector having elements 1 Z I 2 so on Z I p, and alpha is p cross 1. Then H is some unspecified function, but of course, H is greater than 0, because H Z I transpose alpha is the variance sigma I square, and variance is always greater than 0. Then our objective is to test sigma I square is equal to sigma square u for all I. Now, this is equivalent to testing the hypothesis alpha 2 equal to so on equal to alpha p equal to 0, because if under H naught, if alpha 2 so on alpha p these are equal to 0, then Z I transpose alpha is equal to 1 into alpha 1, that is alpha 1. So, H Z I transpose alpha is equal to alpha H for all I. So, in this case all the variances are equal, all the sigma I squares are equal, and we have homoscedasticity. So, the steps for Breusch-Pagan test are: we obtain the OLS estimator B and the OLS residual EI yi minus xi transpose B, and then we obtain sigma curl square equal to 1 upon n E transpose E. Then we regress EI square upon sigma curl square on ZI's and obtain explained sum of squares. And under H naught, 1 upon 2 explained sum of square follows chi-square distribution with p minus 1 degrees of freedoms. Again, I am not going into the details of the derivation of the distribution of this test statistic. Then we reject H naught at 100 alpha percent level of significance if this test statistic half ESS is greater than the critical value chi square p minus 1 alpha. So, the test is quite simple. Then this test is an asymptotic test, and then the test assumes fairly general form for heteroscedasticity. And another advantage with this test is it is quite powerful test. Now, we come to the Goldfeld quant test. So, suppose we have ordered heteroscedasticity. So, we want to test the equality of all these variances against the alternative that sigma 1 square is greater than or equal to so on greater than or equal to sigma n square with at least one strict inequality. Then these are the steps. We arrange observations so that these heteroscedasticities or these variances are in order. Say for example, if sigma I square is proportional to xij square, then we may utilize this information for the ordering purpose. Then we divide n observations into 3 groups, n1, c and n2, so that n is equal to n1 plus c plus n2. In next step, we omit c central observations, and then we run OLS to first n1 and last n2 observations. E1 is the residual OLS residual obtained by running OLS to first n1 observations, and E2 is the OLS residual for the last n2 observations. So, the test statistic is E1 transpose E1 upon n1 minus k divided by E2 transpose E2 upon n2 minus k, and this follows an F distribution with n1 minus k and 2 minus k degrees of freedoms under H naught. So, this test is quite simple and it is a finite sample test. The only problem with this test is the ordering of heteroscedasticity, but if you have some kind of extraneous information, then you may utilize that information. Or if heteroscedasticity is determined by one of the explanatory variables, then you can utilize this information for ordering the heteroscedasticity. Further, choice of C is also a problem. If we choose large value of C, then it reduces the degrees of freedoms, and then this condition n minus C by 2 greater than k may not be satisfied. And if we choose a small value of C, then the test may not reveal the heteroscedasticity, and this is actually the sole purpose of the test, or sole purpose of omitting the ordered middle observations also. There are few other tests also which I am not going to discuss here, like Glaser test and Spearman's rank correlation test. So, in this lecture we have discussed the multiple linear regression model when the disturbances have heteroscedasticity problem. The problem of heteroscedasticity arises when different observations have different variances. In many practical applications, when we apply the multiple linear regression models, we have the problem of heteroscedasticity, and we face this problem in group data also. So, in this lecture we have discussed the effects of heteroscedasticity on the OLS estimator, and then we have developed the FGLS estimators or weighted least square estimators to tackle different kind of heteroscedasticities. In several applications, you may observe that the variance sigma I square depends upon some of the explanatory variables or some other variables, and in those cases you may model sigma I square using those variables. We have also discussed different test procedures for testing the heteroscedasticity. So, I am going to stop here. Thank you.
Hi, I'm Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debayan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I'm interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now, before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with the 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that, I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday? So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits. And as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So, what we did is, for falsification test, we took ear complaints and infectious diseases. Now, ear complaints like if you are deaf since birth or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age, and by weight. We did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So, it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a woman's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol, and your incidence of getting high cholesterol. Now, after this, we went in for a policy implication, and in the policy implication, we tried to find 2 policy implications: what matters and exactly how much portion matters. So, as far as how much portion matters, we have found that on an average, 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So, an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices because it has a impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.